Another class. This is Dr. B, your chemistry teacher, and today we are going to be looking at the infrared spectroscopy, the instrumentation and application. We had already dealt with the principle of the infrared spectroscopy in our previous classes, and we had promised ourselves that we're going to take a look at the instrumentation and application. Do not forget to share this class. It's very important you do so. When you share this class, don't forget to also let them know that they should subscribe so that whenever these lectures come up, it will pop up on their phones and laptops immediately, and they become part of what we are doing beautifully here. Don't also forget that I have a Facebook page, Dr. B Chemistry or Science Classes, and that is going to link you straight to it, and you just need to follow and then you share as well. Then you like and comment. Okay, now we're going to look at what aerospectroscopy, the instrumentation and application, is all about. Remember, we had told ourselves that the aerospectroscopy simply is used for the measurement or detection of functional groups in organic molecules and also in inorganic ions. Now, we also told ourselves that it is simply, in the terms of the principle, is simply the absorption of IR radiations, all right, at a particular level, and that this very absorption of IR radiations at this level always falls around a particular region, unlike the UV visible spectroscopy. And we had also told ourselves that when this absorption happens, something will happen, that usually there is going to be an excitation of the vibrational and also the rotational energy levels from the ground state to the excited state, and that will leave us with a transmittance of radiation that can be measured at the screen, where you can see something like a spectrum that will show, and then you can use that data or information to do what, to do certain work as it is. Now today we are going to look at the instrumentation. How does this actually work? How do we put it into practice? Now let us put down a diagram that will guide us in the explanation. All right, now if we put up a diagram of the instrumentation, is going to look like this. Okay, we have this, and then we have these two, and we have this linking us to a sample container. Okay, to a sample container. We have this also linking us to a second sample container, and then we have this bringing us down to this point. We have the transmitted radiation from here. This radiation links us into what we call a transducer. Remember, we had mentioned this already in our former class when we talk about UV visible spectroscopy. So it brings us to a transducer, and from this transducer we have narrow beams that link us into what we also call a detector. Okay, so we have a detector here, and this will bring us into what we now call the data cell, which you can call the display unit. All right, and this display unit of course will give us information like this. Okay, now so this is our display unit. This is our display unit. This is what we call the detector, and this is what we call the transducer. Or you can call it the splitter. And this is your sample container or sample cell, while here is your reference cell. Okay, and then of course here is your lighting source. Okay, so This is your lighting source. Now when you take a look at what we have here, we have also this, okay, and of course this is your exit slit, while this is your entrance slit. Now at this point here we have something here, and this of course happens to be your monochromator. Okay, this is your monochromator. Okay, so this is a typical diagram that explains the instrumentation of the infrared spectroscopy. So you can see a light source. This is an eye arrow light source. You have an eye arrow light source, okay, that produce light. As it produces this light goes in two ways, two directions. The first one moves to the sample container, the second one moves to the reference cell. Now, before this light moves, it passes through an exit slit. This exit slit allows you to have a narrow beam instead of a wider one. Remember that once the light source comes up, it gives you a wider lighting. So, through the help of the entrance slit, it narrows the lighting and gives you a narrow beam. This narrow beam is going to go through what? A monochromator. And the monochromator will always assist you to do what? To generate the required wavelength of light that is needed to hit or strike these sample and reference cells or containers. Now you have a reference cell or container that holds your sample, and then the light continues. And this light that continues brings itself into a transducer. The transducer or the splitter helps to do what? To split that light to give you the right intensity of transmittance. Remember that once this particular light hits here, there is an absorption, and once absorption takes place, you have the transmitted light that leaves the reference and also leaves the sample. These two lights will converge at the transducer. The transducer will allow you to do what? Will allow you to split the light to their required what? Wavelengths. And then the light will now enter into the detector. The detector will only detect what? The intensity of the transmitted radiation that was not absorbed by the sample or the reference as it is. So this transmitted light will now enter into the display unit, where you have a spectrum that will give you information about what? About the sample that you have used in this particular experiment. But there is something important we need to know. Now we said we have an eye arrow light source. Remember that in our former class, when we discussed the UV visible spectroscopy, we had said that there is a UV light source that is always being used, and it was tungsten. Again, even here, the common light source that is used for the eye arrow spectroscopy is the tungsten light source. So you can use the tungsten. You can use the tungsten lamp to do what? To generate the eye arrow radiations that you can use for your experiments. Now, but the tungsten radiations are always around the region of the near infrared spectroscopy. Alright, so but we have said in our principle that the radiations that are always or commonly used to carry out the eye arrow spectroscopy experiment are always radiations at the mid eye arrow. So if they are the mid eye arrow, you may not have to use the tungsten lamps to do your experiment. You may decide to be making use of what we call a global light source. Okay, there's a global light source you can use, or you can even use the nest. You can even use the nest lighting. Okay, because the global source and the nest globe are the two lighting source that can be used to generate eye arrow spectroscopy, eye arrow radiations at the mid eye arrow, where of course is the frequent source of radiation for the eye arrow experiment. So, but just for your information, tungsten lamps, global source, nest globes are used for the IR spectroscopy. Now, if you come to the monochromator, where of course the monochromator is going to separate that particular lighting that comes from this light source into specific wavelengths of light that can be absorbed by these samples. Now, the monochromator can either be a source of, the source can be a prism or can be a grating type. You can have a prism type monochromator, or you can have what? You can have a grating type monochromator. But usually, prism type monochromators are well used. But there is something very important about these monochromators. If you want to use a prism type monochromator, you may not have to use monochromators that are built from quartz or glass. Remember that in our previous class in the UV visible spectroscopy, we had told ourselves that you cannot use glass, for example, to build monochromators for the UV. The same thing happens here. Quartz and glasses are not used for building IR monochromators. This is because both quartz and glasses have a very high tendency of absorbing IR IR radiations. So if they have that particular strong tendency of absorbing IR radiations, if you use them for your sample, it will not only be your sample that is doing what? Absorbing the IR radiations. Also, the monochromators are also absorbing. In that case, you cannot be able to tell the exact radiations that are transmitted at the end of the day because of the intense absorption. So usually we don't advise that quartz or glass we use for prism preparation. The kind of monochromators that you can use for IR spectroscopy if you are building a prism is usually something like crystals of let's say crystals. You can also use crystals of halogen salts. Yeah, we have others though, but the best ones are the crystals of halogen salts. If you use crystals of halogen salts to build your monochromators prisms, they do not absorb IR. Even if they do, it's quite insignificant. So we use crystals of what? Crystals of halogen salts. Examples of these crystals of halogen salts are sodium chloride. Sodium chloride crystals are very good source of monochromators if you are building them for the prism. Okay, so you have crystals of sodium chloride, you have crystals of potassium bromide, you have also crystals of lithium fluoride, and all of them, all these crystals are used to build prisms. Monochromators prisms for IR spectroscopy. Alright, so you don't use quartz, you don't use quartz or glass. You don't use this. You use crystals of what? Crystals of halogen salts to build prisms for monochromators for the IR spectroscopy. Now that is clear on that. Now, away from that, we had said that once these radiations are absorbed, there are radiations that will be transmitted. Those ones that are transmitted will get themselves into the transducer or the splitter, where they are going to be splitted into the required wavelengths and allowed to pass through the detector, where the intensity of the transmitted light will be measured, and this will be read at what? Will be read at your display unit. Now at that display unit, what you will see there is a spectrum, and that spectrum can either be absorption spectrum or a transmittance spectrum. For an IR spectroscopy, you can have an absorption spectrum or you can have a transmittance spectrum. But usually, what is advisable and what is used in most of your organic chemistry textbooks is the transmittance spectrum. And this is because the IR spectroscopy do not produce spectrums that are maximal. unlike the UV visible spectroscopy. So the IRO spectroscopy does not produce spectra that are maxima. So it is always easier to detect whatever information you want out of the transmitted radiations. Now again, there is a possibility that through IRO spectroscopy you can have all your radiation absorbed by the sample, and if they are completely absorbed, you have a zero transmittance. So usually it's advised that you make use of the transmitted radiation. But let us take a look at what we mean when we say absorption, IR absorption spectrum and that of the transmittance. All right. Now, if after all that you have done, and then you find your results showed at your display unit, they will show in this form. You can have them show in this form. You can have something like this nature in this form, or you can have them being shown in this form. Good. All right. So if they show in this form, let's say if they show in this form, this is actually absorbance. 100% absorbance and 0% absorbance. And this, of course, let's say approximately 3600 cm. Like this is actually your wave number, your frequency or wave number, okay, measured in per cm. So this is the way you get it. You get this information. Now this is the absorbance IR spectrum. And this is the transmittance. This is the transmittance IR spectrum. This is the IR transmittance. So this is also 100% and this is 0%. And this is also approximately 3600 cm. So you can see that you can generate information from the IR instrumentation either as absorbance or as transmittance. But like I said, usually this is the one that is acceptable. So you can use this to read information, and this is simply a peak, or you can call it a band. So there are multiple bands depending on the intensity of transmittance. Now, having gotten here, there is need for us to also know that where you have that your display unit that is displaying this your IR transmittance spectrum, there are different types of spectra. Okay, so the spectra that you get can either be strong spectra, can be medium spectra, or weak spectra. It depends on the intensity of the bands, and that's why we are saying that usually not all the covalent bonds that a compound has that is able to show at the IRO spectroscopic spectrum, not all. It is only those that are polar in nature that can be able to show the IRO spectrum. Not all the covalent bonds in organic compounds that show IRO spectra. It is only those that are polar. We're going to go to that. But all the spectra that are shown, they are shown either as strong spectra, weak spectra, or medium spectra. Now this is what we mean. So you can have a spectra, you can have a spectrum, or of course, that shows this. The one that shows this. You can also have the one that shows this. Yeah. So you can see that this is a strong spectra, or rather spectrum, let's put it that way. This is a strong spectrum or a strong band. Okay, this is a strong band. And then this is a medium band. And this is a weak band. All of them have readings you can get from the data you can generate from them. So this is a typical IR transmittance spectra, because we have 1, 2, 3 here. But for each of these, you have a strong band or a strong band, you have a medium band, you have a weak band. But like I had explained earlier, not all covalent bonds molecules with covalent bonds that generate spectra or bands. It is only the ones that are polar. So what do we mean by that? It simply means that the intensity of any spectra or any band depends seriously, all right, depends seriously on the strength of that particular bond that is taking part in the IRO experiment. That particular bond, the strength of that bond, the magnitude of that bond that is taking part in the IRO experiment is directly proportional to what? To the intensity of what? The band that is formed. So if you are having a strong band or a strong peak, it means that the magnitude of the bond, which must be a polar bond, is what gives rise to that particular band or peak. Then in that case, it means that all strong polar bonds, for example, a carbonyl group, compound that is a molecule that has a carbonyl group, functional group, those kind of molecules are strong polar, they have strong polar bonds, and they will always generate what? Strong bands or peaks. So it means that, for example, this is a carbonyl group, okay, functional group. Compounds with carbonyl functional groups, okay, as they have strong polar bonds, and they will always generate what? Strong peaks or bands. And then you also have compounds that have medium polar bonds. This kind of compound, for example, a carbon-nitrogen triple bond. Compounds or molecules with carbon-nitrogen triple bonds, for example, will always produce medium bands. And it's not just them. All compounds or all molecules with carbon-nitrogen triple bonds, or those that are actually asymmetric in nature, will always produce medium bands or peaks. Alright, so the same thing happens with the weak bands. Weak polar bonds or symmetric bonds, as the case may be, will always produce either weak bands or peaks, or will produce what? Bands that are not visible or observable. For example, molecules or compounds that has this will always produce weak bands. But molecules or compounds that have this kind of a compound, okay, so this is alright. So with a methyl group C double triple bond C, or methyl group, compounds like this will always produce bands that are not observable. They are not observable. But the important thing in my explanation here of these different type of bands or peaks you can get from IRO is that the intensity of any band or peak, that is say strong, medium or weak, depends on the magnitude of the bond, which of course is polar, that is taking part in the reaction. You can go further and further to discuss what is happening around the display unit of the IRO spectroscopy. We can also talk about the types of peaks that you can see. You can see peaks that are narrow. You can see peaks that are also broad. Of course, narrow peaks are always having, they are always sharp. Okay, they have a pointed nose like this. Okay, these are narrow peaks, pointed nose like this, and they are always sharp, and they look like a knife. All right, and then you can also have a broad IRO transmitter spectra where they are not narrow and pointed, but here they appear to be very smooth and appear to be very wide. Okay, so anyhow you look, you see them in the IRO spectrum, it doesn't matter. They can be smooth and wide, so they are broad, or they can be narrow, sharp, so it doesn't matter, they are still IRO spectra. But the important thing is that they are coming out in that way because of the magnitude of the bond that is forming them. And these bonds that are forming them are always described as the IR active bond. This is why I'm going to end my lecture with you today. I don't want to take much of your time. We're going to continue talking about IR spectroscopy some other time in our next lectures that we're going to see. My name remains Dr. B, your chemistry teacher online. Do not forget to share this class. Do not forget to like, comment. Do not forget to subscribe. Share it with your friends. Tell them to subscribe. Don't forget to go to my Facebook page, Dr. B Chemistry Classes Online. You are also going to share them and ask them to do what? To follow, like, and comment. Until next time, it is bye for now.